Unclear how we got this function? Any questions about this function? Are we okay? Okay, so then obviously now I look at this function. It has a maximum and it's quadratic. Now I'm going to ask myself, how do I determine the maximum of a quadratic function? What do I need to do? What do I need to determine? Exactly. That's all I need to find. This value will tell us what? And then I'm going to ask, what will this value tell us? Let's suppose I have the vertex. And let's suppose the vertex is 4, 5, as an example. Not related to what we're doing right now. But what does this say? What does this value represent? Where the maximum is. Perfect. So the location of the maximum is when x is 4. No doubt about it. What does this value will represent? How much is the maximum? So whatever I get will give us the x. Whatever I get here will not give us the other number. It will give us the actual product. So not to be confused, this is not the y, which is the second number in our problem. This is the y that represents the product. So this will be the max product. And this will be the x value that will give the maximum product. So I wanted to specify this because sometimes students think that it's x comma y. So is this x and that y? No. Remember? So if this is the x that we plug in the function, this is the y that we get for that particular x. Is that clear? Okay, perfect. So now I have to remember how to find the x-coordinate of the vertex. How do I find the x-coordinate of the vertex? Always remember the quadratic formula. Once you remember the quadratic formula, you remember what to exclude and what is left for the x-coordinate of the vertex. Right. Everything that is not on the square root, that will always give us the x-coordinate of the vertex. Thank you, Ryan. Okay, so then minus is in front. Now, be careful. This always has to be in descending order, because if it's not in descending order, you may make a mistake in identifying A, B, and C. So always keep polynomials in descending order. Okay, perfect. So B is... No. So the negative is outside. B is positive 16, but you're right. You read this. I understand. Just making sure. So B is positive 16, and 2 times A is 2 times this number, which is negative 2. So the answer is 8. So if x is 8, I can determine the other number. I'm not talking about the maximum product just yet. I can determine the other number. What will the other number be? 8. And now I have two options. I either go with this x and plug it in here, or say, well, this function is the product of these two numbers. So what is the product? You'll get the same answer no matter what. You either multiply these two and put the answer here, or you go back with x and say negative 64 plus 16 times 8, and you have to get the same answer. So what will the answer be for the maximum product? And then we'll write the final answer for the problem. Perfect. So here is the complete answer. Let's write it together. The maximum product of two numbers that sum up to 16 is, can anyone tell us? Awesome. Full stop. The numbers that yield this product are, exactly, x equals 8, y equals 8. But all this was possible because we understood how a quadratic function works. Yes, Brian?
How'd you get 64?
Okay, so I have two options for 64, correct? So I have one option of determining this y value by plugging in 8 here.
8 into the original equation?
Of course, remember the vertex.
Okay.
Once I find x, how do I find the y coordinate? This has to be f of that x. So that's one option. So negative x 8 squared is 64 with minus in front. Careful how we square. So 8 squared is 64 with minus in front. So let's do that. So p of 8 is negative 64 plus 16 times 8. 128 minus 64 is 64. The other option is, you can say, forget about the function because I know how I created it. I created this x times y. I have x, I have y, multiply them to get that number. But it's the same thing. It doesn't matter how you come to the conclusion of that. We normally plug it in. But since we created the function and we know how we created the function, it's easier to find the other value, the other number, and multiply those two. How and why? Because, let me go back for a second. What happened here? Oh, okay. So that's how we created the function. P of x comes from the number x times the number y. Once I have x and y, I'm done. Or I say, okay, so how did I create this? I have 8, and I have 16 minus 8, so 8 times 8 is 64. So one or the other. Perfect. Okay, so let's see if we have anything else. I personally don't have anything else to say about 3.1 unless you have questions, unless you say I need this or I need that. If you don't say any of that, then we'll move on to 3.2. There are a lot of applications with this model, quadratic model. When we review for the test, we're going to go over other problems. Unless you find something in my math lab and you bring it to class, I strongly recommend if you find something in my math lab, a word problem that you would like us to work on in class, please bring it to class, okay? So you think we're ready to move on to 3.2? Okay. Like with everything new, moving on, this is completely new, unless you took this course before. It should be completely new from this point on. Okay. Like with everything new, totally new, you know me, I talk a lot, so it's going to take me 10 minutes to explain one thing. But when we do the second problem, it will take us a minute or two. So bear with me with the first example, because it will take a while. Okay. So section 3.2 deals with polynomials of higher degree, which we have not seen before in this detail. We've seen polynomials degree 3. And what is the polynomial degree 3 that we've been working with doing transformations in chapter 2, section 2.5, and we also talked about last week again. What was the third degree polynomial function that we know almost everything about? Exactly. We know this. This we know. We don't know x to the 5th. We don't know x to the 7th, right? But we know x cubed. Okay, perfect. So that's all we know kind of moving forward. So polynomial functions of higher degree than 2. Like 3, 4, 5, 6, and so on and so forth. Because degree 2 was already discussed in the previous section, quadratic functions. Now, if you remember, you don't have to write this unless you want to. For quadratic, we had a long list of 7 items, right? Okay. Obviously, I should have mentioned domain, but it's clear. All polynomial functions have domain or real numbers. Then we looked at, just for a quick refresher, then we looked at the vertex. Then we looked at X-intercepts, if they exist, if, and you know what I mean by if. Y-intercept. We looked at the axis of symmetry. We looked at max-min. And the last one was range. Okay, by comparison, we're going to start now with a cubic function. And then we're going to look at maybe one more example with a fifth, and then we'll come back to the even degrees. Okay, for any other polynomial function, we will have the same list. We will have domain, but there will not be any problem. What do I mean by that? What will be the polynomial degree 3's domain? Correct. There will not be a vertex, no vertex, ever again. When we say vertex, we only mean one thing: the maximum or minimum of a quadratic function. I'm done. We're done moving forward. Okay? The same thing with graphing using the slope. What is the only function that I never recommended, but it can be graphed using the slope? Which function can be graphed using the slope? Linear. Done. No other function can be graphed using the slope. That's why I never ever emphasize that method. Okay, so for polynomials, the domain will be the first issue. No vertex, no anymore. The x-intercept or intercepts. The y-intercept, of course. No more axis of symmetry. There's no such thing. Those graphs are not symmetric with respect to their own axis of symmetry. None. So no axis of symmetry. Max, min, yes. Range, yes. However, we have to add a few things here. Number one that we have to add is end behavior. What is that? We'll get to it in a minute, which we did not discuss in quadratics. There was no need for that. We also add here max possible number of turns. Totally new. How many turns does the quadratic function have? Look at my hand. I'm graphing a quadratic function. How many turns does it have? One turn. One turn. One turn. So we're going to talk about maximum possible number of turns. And one other thing we have to add here, multiplicities. For multiplicity, multiplicities of X-intercepts. We have not seen this before. We never talked about end behavior. We never talked about maximum possible number of turns, and we never talked about multiplicities of the X-intercepts. So this is totally new. Okay, so I would like to choose. We're going to start with a cubic function, odd degree, and then we're going to look at even degree. Before we choose an example, I would like to talk a little bit about these multiplicities and what they mean. Okay, multiplicities of X-intercepts. What does this mean? And why is it so important? I referenced to it a long time ago. And I said, keep this in mind, keeping this in mind, but I didn't tell you what it was. Okay. So let's look at a few scenarios. Let's suppose I have a function that crosses the, so we're talking about x-intercepts. Everything happens on the x-axis. The discussion that we have right now, it's all about x-intercepts. So let's suppose, and you'll see that once you see it, you'll remember, because I said that a couple of times. Okay, so here is a function that crosses the x-axis like this. Here's another function that we just talked about a minute ago with a cubic x cubed that does this. Still only one intercept, but it takes its time. It's not rushing to cross, if you want. It takes its time. Still one intercept. There's no more than one intercept in there, one cross, but it takes its time. And here's another possibility. And here's another possibility. And I can go on forever, right? Flatter even, and so on and so forth. So now, what does this all mean? Every time the function crosses the x-axis, it has a number of x-intercepts at those spots that is odd. So how many solutions x equals 1, let's say, does this function have? Only one. How many solutions x equals 2 does this function have? The answer is 3. So if this is 1 in my example, and 2 and 3 and 4, so this is what it's called an odd multiplicity. And I will write here, this situation is 1 solution. This situation is 3 solutions. It sounds difficult right now. You will see it's not in a minute when we start looking at examples. When the function turns, what do you think? What type of multiplicity will this be when the function turns? And think of x squared. So this is what type of multiplicity? Can it be odd? No, because the function does not cross. What could it be? This is not connected to the even symmetry or odd symmetry at all. This is just another way of saying it will turn, and it has 2 solutions here. So this is an even multiplicity. So this one, the solution x equals 3, appears twice. What about here? The solution x equals 4. How many times do you think it appears? It cannot be twice because this is a quick turn and this is a slow turn. It cannot be an odd number because the odd number, the function crosses. So it has to be, if it's not 2, it must be 4. So x equals 4, 4 times. So let's go back. This is like the linear function, right? It crosses, and there is no other explanation. There is x equals 1, 1 solution. What about this? It crosses, but it takes its time. It's not a simple cross, but a slow cross. It cannot have an even number of multiplicities because it crosses. So it has to be, if this is 1, this is 3. These two are even multiplicities, which means x equals 3 will appear twice as a solution. And here, x equals 4 will appear 4 times because see the difference between these two? Quick turn, slow turn. Okay? Not a big deal. Let's see how we apply this in graphing. So we are on page, if you have your books, you can, I'll let you choose. If you don't have your books, then I will choose. Page 378. Do I get to choose? Is that a yes? Yes? Okay, I will choose then. 53 caught my eye. F of x equals 3x squared minus x cubed, and this is 53 on page 378. Okay. One other thing I wanted to add to our list, because I don't want to forget, It makes a big difference, which we didn't do in quadratic because it was very clear. I want to add to the list degree. However, these two are connected. I'm going to go through the list again. I'm going to write the list one more time. This is just a synopsis, just the idea, what we need to look at. Okay. So first of all, I have to identify what type of function this is. Of course, the question is graph it. That's all they're asking us to do. Graph this function. So, what type of function is it? Yes, it's polynomial degree 3. Perfect. Cubic, polynomial, degree 3. That's the first thing. Number 2, domain. No discussion there. All the numbers we know, all polynomials. They are not giving us any headaches. Number 3, since we identified that the degree is 3, comma, maximum possible. I'm not saying that it has to have this number. This is possible. Maximum possible number of turns is degree minus 1. Since the degree is 3, how many turns can this function have? Not more. It doesn't have to have that number, but it cannot exceed that number. How many? Indeed, it cannot have more than 2 turns. Step 4. X-intercepts. And I will make it together with and their multiplicities. X-intercepts and their multiplicities. Okay, so I'll write the function one more time here. 3x squared minus x cubed. What will you do first? Kind of mandatory. Say it again. Descending order, absolutely. That's the first step. So in descending order, perfect. And I see that I can factor out something, including the negative leading coefficient, which is crucial right now. So what will I factor out? Perfect. What is left in parentheses? X. Is that clear? Is that clear why? Perfect. Okay, how many solutions will you give to, or how many x-intercepts does this function have? And what do I have to write? How do I find x-intercepts for any function? I have to set something. Very good. So solutions of f of x equals 0. I have to write myself a note, not to forget. This is what we always did with polynomial equations. How many solutions I have to find no matter what? Very good. The degree is 3. I must find 3 solutions. I already factored the left-hand side. I'm going to replace f of x by this. I will multiply both sides by -1. I refuse to solve like that. And now I'm ready for you to give 3 solutions. This equation obviously has 3 solutions. Very good. As expected. Yes? That's why we did this in section 1.6 for this. So can anyone give us those 3 solutions? 3. Okay. That's what happens. We get to sometimes step 10 and we forgot step 1. We can't do that. That's why I'm asking you to redo those tests every weekend. Very important. So, can anyone give us 2 more solutions? Very good. X equals 0, x equals 0, and x minus 3 equals 0. Awesome. Okay, so what is the multiplicity of the solution x equals 0? How many times does x equals 0 is a solution or a 0 of this function? That's the multiplicity for solution x equals 0. What will happen? What will happen at x equals 0? Case 1, case 2, case 3, or case 4? 1, 2, 3, or 4? Exactly. At x equals 0, the function must turn. Why? Because it has x equals 0 appearing twice as an x-intercept. How can it cross twice? No, it won't. It won't cross twice, but that is an indication that the function will turn. Okay. What is the multiplicity for x equals 3? 1. What will that case be? Case 1, case 2, case 3, or case 4? Exactly. So when we get to graph the function, we know what happens at those points. Perfect. Awesome. Number 5 on the list. Any questions so far? Y-intercept? It's a moot point here because x equals 0. We already found that y equals 0 when x equals 0. So if you want, you can plug in 0, 0, and we get 0, which we already had from before. Any questions? Okay, number 6. Let's talk about end behavior. For this problem, I'm listing everything step by step, but moving forward, we're going to use a chart table, and we're going to put all the information in there. Okay, so let's see what end behavior represents. Okay. Does this function have an odd degree or an even degree? Odd. Because it's an odd degree, there are only 2 possibilities. By end behavior, first of all, let me clarify. End behavior means where is this function going as x approaches negative infinity and when x approaches positive infinity? At the very end. That's the end behavior. Okay. But since the degree is odd degree, there are only 2 options for the end behavior. One is this, coming from negative infinity to going to positive infinity, like the linear function with what type of slope? Positive. Very good. Or this is the other option, coming from infinity and going to negative infinity. There is nothing else. And it all depends on the leading coefficient. Right? The leading coefficient here is the slope, which is positive. The leading coefficient here is the slope, which is negative. So now in order to find the end behavior for this function, all I have to do is look at the leading coefficient. Since the leading coefficient is negative, it's this situation. Leading coefficient less than 0. Leading coefficient greater than 0. And that's the end behavior. So it's not this, but it's this. We're going to put everything in a table in a minute. Number 7. Symmetry. Not the axis of symmetry like quadratic, but symmetry. Remember, symmetry, we have 2 types, odd or even. That's why we studied this in chapter 2. For chapter 3. For odd, how much is f of negative x? Well, what does f of negative x equal to for odd? Awesome. What does for even equal to? So f of negative x equals f of x for even, and f of negative x equals the opposite of f of x for odd. So let's just see if this function is symmetric. It's nice if it is, but it doesn't have to be. Okay, so I'm going to determine what? Like we always did. I have to determine f of negative x. So when I plug in here, negative x, so I have f of negative x, which is negative x to the third plus 3 times negative x squared. Let's see what we get. Sure, I'll see you on Wednesday. Okay, so negative x to the third. Negative x times negative x times negative x. What does that equal to? To the third times negative x times negative 1 in front. Awesome. How much is negative x squared? Times 3 is positive 3x squared. So now I'm asking myself 3 questions. Does this equal the original function? Does this equal the opposite of the original function, which will be x to the third minus 3x squared, or none of the above? Is this the same with the original function? No. So the function is not even. Is this the same with the negative f of x? Are they the same? No. So the function is not symmetric. Number 8, max min, but this cannot be done without the use of the calculator. Only TI 84, 85, 86, 81, 82, whatever you have. I know it's a lot, but we are going to put everything in a table that will give us all the information at a glance, and we're going to be able to graph it. So let's summarize everything we have so far. And let's create a table. And here's our table. Like we did with piecewise defined functions, like everything, we need to show the work. So the domain, as you told me, negative infinity to infinity. I'm going to write on the side symmetry, none. That's the only thing that does not fit in the chart, in the table. I will have 0 and 3. I will write 0 underneath because they are both x-intercepts. I will write myself a note above 0, 0 that this must be a turn. I will write a note about 3, 0, and I will say this is a regular cross of the x-axis. And I discovered the end behavior as being positive infinity to negative infinity. That's all I need. All these pages now mean nothing anymore. Yes, I have not determined the max min, but my only chance is with a calculator. And you can say, do you have enough points? You can determine any more points that you want. You can plug in -1, you can plug in 1, 2, 4, 5, whatever you want. There is no need. And let me show you why. But it's acceptable. I don't want you to waste too much time on this. I shouldn't say waste. I should say spend too much time on this. So I have 0, 0. I have 1, 2, 3, 0. We know that this function cannot turn more than how many times? It doesn't even have to turn that many. But how many times maximum? 2, because the degree is 3. Perfect. So the function is coming from positive infinity down to this point where it turns. It must do something here, we'll figure out in a minute, because it comes back and crosses at 3, 0 and going to negative infinity. One more time. It's coming from positive infinity and it turns at 0. It must go to a maximum because it can have 2 turns, to a maximum value, and then it comes down, crossing at 3, 0, going to negative infinity. Now you can say, how do you know how high is this? What if it's this? What if it's this? I don't know. That part I don't. That's why I have to find the max min with the graphing calculator. So let's put in the graphing calculator. So first of all, this is f of x, which is negative x cubed plus 3x squared. Can anyone give us the range of this function? Very good. We know absolutely everything about it the moment we get the maximum. And sorry about this. So in y equals, please put in the function. Negative x cubed plus 3x squared. In y equals negative x cubed plus 3x squared. You didn't mean that, of course. Okay, so now I take a moment and think. I already graphed the function. I want to change, I want to come up with the best viewing window. Do I really need to see negative 10 on the left-hand side of x? No. Do I really need to see 10 on the right-hand side of x? No. How high I go, I don't know. But for sure, I don't need a lot of under the x-axis. So I'm going to go to the viewing window because I already graphed the function. And I'm going to say negative 5 to 5 with a scale of 1. Y minimum, I don't really care that much. Negative 4 is good enough. I don't know how high I should go. I already have this feature here that you probably don't, right? So I'm going to say 7 and see what happens. And then click on graph. Here it's coming from a positive infinity. It turns as expected. It reaches a maximum. It crosses at 3, 0 and go into negative infinity. And that's exactly what we know. And this is exactly what we graphed. We really didn't need to do this with the calculator. So the only thing we want now is to determine this maximum. I see that this maximum, it appears that is at 2, but I can't be certain. I'm going to give the calculator a window, like between 1 and 3. Here's how I do it. Second and calc. Since I want to determine a maximum, I will choose number 4. I will say to the calculator, the left bound, okay, the left bound is 1. And it presents this line saying, okay, from here, make sure, yes, from here. And to 3. So the right bound is 3. So now the calculator is asking me, are you sure? Is this where you want to determine the maximum? Yes, yes. I don't want to guess. I'm just going to press enter. Yes, that's true. I want you to give me the maximum between 1 and 3 for x. And the maximum is 1.99999, so it's clearly very close to 2. So the local maximum is 2, 4. I'm going to plug in the function and see what I get. So negative 8 plus for x equals 2. Negative 8 plus 3 times 4 is 12. Obviously, that's it. So I found the fact that I got negative 1.99999, this is the error of the calculator. So I go back to my table, and I will put 2, 4, and say local max. There is no need to go back and adjust the graph. That's all I needed you to show. I didn't know where the maximum was. Nobody does. We do in calculus. We have methods of doing this in calculus without a calculator, but not in algebra. Any questions before we look at another odd degree function? Any questions? Okay, everything is the same for the 5th degree. Everything is the same for the 7th degree. Everything is the same moving forward. Once you understand this one, you will have no difficulties with any odd degree. So let me pick, let's say, I can't find a 5th degree. Okay, I did. Here it is, 51. Same page. F of x equals 6x cubed minus 9x minus x to the 5th. Instead of listing all those, let's go ahead and start the table. You can always go back to the list, but once we fill out the table, we know we haven't missed anything. The only thing that is not in there is the degree, the number of turns, and symmetry. Everything else will be in the table. Domain, please. Correct. Degree. 5. Max possible, not necessarily, number of turns. It doesn't have it, but it cannot exceed what number? 4. Let's arrange it in descending order and identify the end behavior. So f of x will be negative x to the 5th minus, awesome. Perfect. Good. Since the leading coefficient is negative, remember it behaves like the linear function with a negative slope. That's all you have to remember. It's an odd degree. It can have this option or this option, depending on the leading coefficient. So which one is the end behavior? Perfect. Then we have to identify the x-intercepts. What do I have to do first? Work a little bit on the function. Prepare the function a little bit. What do you think I'm going to do? From the little you know about me. Good. What else? Very good. So we have x to the 4th minus 6x squared and plus 9. Now I look at this inside trinomial, and I have to dig deep. Why? What type of equation, I shouldn't say equation because it's not an equation yet, but what type of polynomial is this? X to the 4th minus 6x squared plus 9. How many solutions will it have when I set it equal to 0? Perfect. What type of equation will that be? We've seen this before. In quadratic in form, exactly. So when I set f of x equal to 0, see how everything from chapter 2 is coming now? So when I set this equal to 0, I have negative x to the 4th minus 6x squared plus 9 equals 0. Of course, I will multiply by negative 1. I cannot do it in a function, but in an equation, I can multiply by negative 1. So I get x, and then x to the 4th minus 6x squared plus 9 equals 0. How many solutions again? I need to write them on the side so we don't forget. 5 solutions. Here's the first one, but 4 more have to come from here. But how do I do this? How do I find those 4 solutions similar to chapter 2? I will change x to the 4th minus 6x squared plus 9 equals 0, saying let t be. Very good. And now the equation becomes t squared minus 6t plus 9 equals 0. Now I have to remember what this is. That's why we did this, if you remember, on the first day of classes. So t squared minus 6t plus 9. Yes, you can use the quadratic formula, but this is very easy to factor if you remember the special product. Yes, you too. Thank you. Very good. Awesome. So this is t minus 3, everything squared. So we get 2 solutions for t. but they are the same. T equals, we cannot talk about multiplicities for t. I have to wait till I get to x. So, but t equals x squared. So then we have an equation that is x squared equals 3. How do I solve such an equation? It's a quadratic equation. I have 4 methods, but there is one specific one that I should be using. Take the square root indeed. So x equals, if I forget something crucial, then I'm not going to get all solutions. Plus or minus the square root of 3. But I'm expecting 4 solutions. So I have another equation that is x squared equals 3. And I will get 2 more solutions, plus or minus the square root of 3. So one solution is 0. 2 solutions the square root of 3. And 2 solutions negative the square root of 3. So I go back to the table. First of all, I have to identify the multiplicity of 0. How many times? 1. So I only have one solution s equals 0. What will the function do at that point? Cross indeed. We don't know if it's up and down. I don't know, but it must cross. So from here, it's very clear that I have x equals the square root of 3. How many times? Multiplicity, 2. And the square, negative the square root of 3. Multiplicity, 2. Now let's count multiplicities. 1 plus 2 plus 2. Do I get 5 solutions? Multiplicity 1 plus 2 is indeed 5 solutions. So I go back to my table. I put 0, 0, which is a cross. I put negative the square root of 3 and the square root of 3 with 0 and 0, which is what? So multiplicity 2. Multiplicity 2. What does that mean? What will the function do there? Exactly. Max min with the graphing calculator. And the last thing that I need to, and it's not, doesn't have room in the chart, is symmetry. So I have to find f of negative x, which is negative x to the 5th plus 6 negative x cubed minus 9 times negative x. So negative x to the 5th plus 6 negative x to the 3rd minus 9 negative x. So negative x to the 5th power is, what do we get? Negative x to the 5th times negative 1 in front. Very good, awesome. Negative x to the 3rd is negative x to the 3rd times 6 will be negative 6x to the 3rd. And this is the product 9x. So now remember we have 3 questions. Does this equal f of x? Does it equal the opposite of f of x, which will be, I'm going to write it here, x to the 5th minus 6x cubed plus 9x, or none of the above? So it's, they're not the same. So this, it's odd indeed. Not this, indeed odd, which means the function, I'll have to make sure that I graph a function symmetric with respect to the origin. So if the function has a maximum or minimum on this side and it's symmetric, I only have to copy it across the origin. I don't have to determine it with the calculator again. Because if the maximum here is 1, 2, what will be the minimum here? Negative 1, negative 2, correct? I don't have to calculate. I don't want to waste my time if I know it's odd. That's why we are trying to check. We check whether functions are symmetric. So if it has a maximum here at 1, 2, across the origin, it will have negative 1, negative 2. So I don't have to waste my time working on that. Perfect. So now I will make myself a note. The function is odd. Make sure I graph a function that is symmetric with respect to the origin. Okay, that's all I need. Everything else is just work. You can go away for a moment. So let's give it a shot. And then we check. Now, I know we are tempted to grab the calculators and look at, no, you're not going to remember what to do. You're not going to understand the graph. By simply looking at the graph and then trying to figure out portions and how to fill it in, it's not a good idea. Let's discuss the graph and then check our understanding. Okay, so I have to plot this point, which is roughly negative 1.7. So negative 1.7, I'm going to say it's here. Then I have to plot this point, which is here. And then on the other side, 1.7, which is here. Okay. The function is coming from infinity, and it has to turn here. Obviously, it has to go to a maximum. It comes back, and it crosses straight. No question, no slowing down, crossing straight. It has to come to a minimum because it has to be symmetric. The same maximum here, same minimum here. And then comes back and turns at this point, going towards negative infinity. One more time. From positive infinity, it turns, but it has to go to a maximum. Crosses, has to come to a minimum. Turns to go to negative infinity. How high is the maximum? No clue. But it's the same here and here. Just that this side will be at negative. So let's do that. So coming from positive infinity, turning at this point, has to have a maximum. Crossing normally, has to have a minimum, and these have to be the same. If this is here, these have to be opposites. So then it comes down and crosses and going to negative infinity. Just to make sure, it's degree 5. What is the maximum possible number of turns again? 4. 1, 2, 3, 4. So the only thing I need as a clarification with the graphing calculator is this point. How high? And automatically I will get this point, how low and where. And this is the function f of x, negative x to the 5th plus 6x cubed minus 9x. So